So yeah, before I begin, MapReduce and Spark are two frameworks or platforms to perform this computation with a distributed system. So you have some job and you have a large amount of data, gigabytes or maybe even terabytes and petabytes of data, and you want to process that on multiple machines, then you can use MapReduce and Spark. So let's start with MapReduce. So MapReduce is a programming framework for distributed analysis of large amount of data. So it was originally developed at Google. I already shared this link in 2004. And Hadoop is the open source implementation of MapReduce. So there's also an implementation available at Google, but we don't know the details about that. And obviously, that also has evolved because, yeah, that was back in 2004, and now we're almost we're 17 years later. So the framework is for reliable, scalable, and distributed computing. And so with reliable, we mean available, fault tolerant. Scalable, we mean we can scale to thousands of different nodes, and yeah, distributed computing. So it's used for a bulk analysis and especially for offline batch processing by data scientists. It supports both analytics and distributed machine learning. Use cases are if the data does not fit onto disk or in memory of a single node, and also that data operations can be expressed in an embarrassing parallel way. It's also the basis for more recent developments in stream processing, such as Spark. What is the Hadoop stack? So the Hadoop stack is actually what you install. Given your cluster of computers, you need to install these three different pieces of software. So first we have the resource manager and scheduler. Usually that's Yarn. So the resource manager kind of controls all the clusters. So it checks if all nodes are still available, that nodes haven't crashed. It makes sure that there's communication between each nodes for executing each job, things like that. So it's basically scheduling your jobs on that cluster, managing the resources. Then you have the distributed file system. So HDFS is the Hadoop file system, is the open source variant of Google's original proposal. We talked about that before during the NoSQL lecture. And then we have MapReduce. And so these three pieces of software work together, and they take care of partitioning your data. And so that's more the task of HDFS, making sure that there are messages between all your clusters, all your workers. They make sure if hardware fails that you recover from that, and they schedule your program, which is made of map and reduce tasks on the nodes in your clusters. And so once you have this installed, actually for you as an end user, you only have to define your program, so your mapper and reducer tasks, and also the amount of resources you want to use on the cluster. So if you want to use 10 or 100 servers, and then Hadoop takes care of the rest. So you don't have to worry yourself about hardware failure. That's something the software does for you. So this is the most essential part. So the MapReduce paradigm. So it's based on the assumption that most data processing tasks can be decomposed into multiple two-step stages. And so each operation is a two-step stage, and you can chain different operations after each other. And so the first step is a map function, and the second step is a reduce function. And the map and reduce functions you need to program, and then they are distributed over the network, over the cluster, and applied to chunks of data. And so the data is partitioned and also replicated. So usually it's replicated on at least 3 servers. That's the default in Hadoop file systems. So if one server crashes, you still have the same data on 2 other servers in a redundant way, and it's also partitioned. So the data is divided, and not all data is stored on a single node, as that would not be efficient if you have large amounts of data. Not possible even. We assume that data samples or records are represented as key value pairs. So that's like in Python, you have a key and maybe a property like name or something, and then a value which is the actual name. Or the key can be a city, and then the value can be the specific value of that city, things like that. And so we represent our input as key value pairs, and then in the map step, you simply transform the data. And so you take as input a key value pair, and you output a different key value pair or a list of key value pairs. So that's the map step. And then in the reduce step, you reduce. You specify a reduce function, and that's to apply to each group of key value pairs having the same key. And so you can, typically you aggregate all values that have the same key. And so, for instance, if you group on a certain key, then you have a set of values, and then you output another key value pair, and that is some kind of aggregated value over these values. That can be the sum or something like that. So that's the abstract definition, and we'll see a lot of concrete examples in the next slides. And so, for instance, the word count example, which is the example that's always used when introducing, mostly used in MapReduce in different textbooks. And so, as input, you have a full sentence, and then you have the map function, and the map function splits this sentence, for instance, on spaces, and produces a key value list. And so here the key is a word, and the value is a 1 if the word occurs in the sentence, or otherwise, it's 0 or it's not included in the key value list. And so that's the map function. And so here you map, and you take this sentence and produces a list of key value pairs. And obviously you can have millions of sentences, and then the map function will just count, just create for each word in each sentence a single key value pair. And then you have the reduce function. So the reduce function groups on all pairs with the same key. And so for instance, the might occurs twice in this sentence. So you group on the, and then you have you compute your reduction function. In this case, it's just the sum of the counts. So the occurs twice, so you compute it like that, and bank also occurs twice, and the other words occur once. So that's a reduce function. So what are the properties of a reduce functions? There's no guarantee on the order of the input values. So if you have a certain, if you group by a certain key, and then you have this list of values, and the result of your reduce function should be independent of the order of those values. That's an important property, because if you have no guarantee on the order, that means you can run it in parallel on different nodes, and the order when you evaluate what doesn't matter. So for instance, a sum, for a sum, the order of the terms doesn't matter. So sum is always a good reduction function. The output value of the reduce function should be the same type as the values of the map function, or as its input actually. And so the map function should produce some key value structures, some list of key value pairs, and the type of the value should be the same. The output value of the reduce function should be of the same type as the input. And so Doesn't have to be a simple primitive value. It doesn't have to be an int or a float. It can also be a dictionary or something like that, but it has to be of the same type. And so, for instance, if A, B, and C in the reduce key ABC are dictionary, then the reduce function should also output a dictionary. So it's a distributed programming paradigm. And so the framework makes sure your input data is partitioned into smaller chunks and also replicated using Hadoop file system. So it's easy to see that the map and reduce functions can be applied to their assigned data chunk in parallel. So if your data is partitioned in 4 chunks and stored on 4 different nodes, it's easy to see that the map function can just run on each node individually, and the reduce function combines data after the map function of several nodes. And we'll see that in the next slides. Some examples. So for instance, here's an example, and we have a debit and a credit account, and then the amount that is transferred. And so the first row means from account 123, we transfer 100 euros to the credit account 456, something like that. And what we want is to compute the total debit amount per account. For account 123, this is 100 plus 200, that's 300. For account 456, that's 275. And note, we have this colored, we colored each row, so that also in this case signifies on which node it is stored. So for the first account, for account 123, all data is on a single node, so you can easily compute the sum there. But for account 456, some rows are on one node, and some rows are on another node. So that's also shown here. So we have in our entire data sets. Here it's just 7 rows, but normally for MapReduce that would be millions or billions of rows. And then so the data is partitioned. In this case, it's partitioned on 2 nodes, as shown here. And then if you write your map function, which splits each rows and takes the amount per debit account and creates a key value pair of that map function is run on part of the data on node A and part of the data on node B. And so that's here is some pseudocode how the map function would look like. And so as input you have this row from a comma separated file, so it's a string, and the first part is the debit account number, the second part is the credit account number, and then the third part is the amount. And so what the map function do is it takes this line as input, it splits the line on the comma, and then you have the debit account and the amount. And in this case, we're not really interested into the credit account, so we ignore that. We transfer the amount since it's an integer, and then we just return a tuple. And so that's just parsing the data. And so for every debit account and every transfer, we have this key value pair, where the keys is the string code for the debit account, and the value is the amount stored as an integer. So that's the map phase. And then we want to take the sum for each credit account. So for the first, so that means we group by each key. And so for account 123, we group by that key, and then we get a list of values 100 and 200. For the third row here, that's account 456, we see the data is distributed. So during what MapReduce will do, it will do something called shuffling. So during the group by key phase, it will look at the key value lists in each node, and it will transfer data from different nodes to a single node. So here 456 for account 456 we have 3 values, and the first value 100 actually is transferred from another node. So that's called shuffling, and that's necessary because we don't know before that all data with the same keys on a single node. We cannot guarantee that, so it has to be communicated. And then of course after the group by key we apply the reduce function, and the reduce function is just a sum in our case. And so that's then computed on the first node for count 1, 2, 3, and on the second node for 4, 5, 6, and 7, 8, 9. And finally, we can collect or save all the data from different nodes. So here's an example of the pseudocode for the reduce function. So we have a common key here, which is the debit account. Then we have an iterator, which is a pointer where you can loop over, and you just loop over all values, and you take the sum, and then you return the key, so the debit account code, and then the sum of these values. And as noticed before, so the grouping of all values with the same key is done by the framework. So you don't have to, you can take abstraction from the fact that that's executed on 2 different computers, and that the data is transferred from the first node to the second node with the group by key. You can, that's all done by the framework. So MapReduce lets you evaluate parallel data computation tasks without worrying about hardware failures and possible data loss that can result from that. It also automatically splits the problem in several tasks and coordinates the parallel and distributed execution. And so there's a lot you can get if you just specify your map and reduce function. All the rest is done by MapReduce. Some number of map tasks are given to 1 or more chunks of data from a distributed file system, and so it depends on the map task where it is evaluated and where the data is stored. But the map task is perfectly, it can be perfectly running parallel on each partition of the data set, stored on a different nodes. And then that map task has to transform that chunk into a sequence of key value pairs, as we have shown. And the way the key value pairs are produced from the input data is something you code. So you write a map function, so you specify how you're going to transform your chunk of data into a key value pair. And then the key value pairs from each map task are collected and sorted or grouped by key, and the keys are then divided among all the reducer tasks. So all key value pairs with the same key end up at the same reduce task. So that's something the framework does for you. Make sure that it groups by key, and even if some tuples are stored in different nodes, the framework will make sure that reduced task gets all values from possibly different nodes. And then the reduced task takes a key as an argument and then combines all the value associated with that key in some way. And the way you combine values is also something you determine yourself in the code by writing the reduce function. So that's how it works. Here's an example in PySpark. So PySpark, or Spark, has a library in Python which is called PySpark. And Spark, you can see that as an extension of MapReduce, but it also offers a map and a reduce by key function. So it has, in this example, it has the same implementation as you would have in MapReduce. So I have an import statement, then I have 2 functions I'm going to ignore for now. And then you have a text file containing all the transactions. So transaction CSV would look like this, like here, shown on the left. So these simple strings containing the debit, credits, and amounts. So that's the input to Spark, this text file. And then you have your map and reduce by key functions you call on the RDD variable. We'll talk later what that exactly is, this RDD variable. And so the map function takes a line as input. It replaces this quote character, because you have to quote at the beginning and end of each line. Then it splits the string on comma, so you have 3 different values, and then the amount value you transfer to an integer. And then you return a single key value pair, and so the first element is the account code, and the second, the value element is the amount stored as an integer. And so first you map that, and then you have your reducer. So the reducer function just takes 2 values. So in this case, it's the total amount, and you just take the sum of those 2 amounts. Okay, so in code, it's actually quite simple. You just call reduce by key, and then it will group on the keys, so the debit account codes, and then take the sum of all values, and that's it. So if you run this, then you have your answer. But this can then be processed. In our case, also for the practice session, it's all toy examples, maybe containing 10 or hundreds of rows. But you can run this program in parallel and process gigabytes or terabytes of transaction using this really small and simple program. So that's nice. And then you have the shuffling and sorting processes. So I explained before what shuffling is. So one of the strengths of the MapReduce paradigm is data locality. So the code is moved to where the data resides. The code is executed on the node that contains your data. And that's important, because otherwise you would have to copy your data all to the same machine or something, and that would be much slower. So that's the data locality principle. However, between the map, for map, it's easy to see that you have all the data that you run your map function on a partition of your data on a single node. But for the reduce step, some type of shuffling process takes place. Shuffling is actually a bad name because it implies something random. This isn't really a random process. It's just communicating rows to one node. So after your map function, all rows which have the same key, all key value pairs which have the same key, are transferred to a single node. So that you can call your reduce function, and that you have all values associated with the same key. Okay. And the rest I explained. So here's an example of that. So again, we have the word count example, and here you have 2 nodes, and then you count the number of words in each sentence, and sentences are stored on different sentences are stored on different nodes. And then after you have counted you have computed which words occur in each sentence, then you have to group by key, and then you take the sum of counts after the shuffling phase. So for example, if on node 1 you have a sentence that contains cookie, and in node 2 you have another sentence that also contains cookie, during shuffling you will make sure that these are both, after that group by on key, you will count that value and transfer data between nodes. Okay. So that's how it works. And then given that all values of the counts of the word in each sentence are grouped by key, you can reduce it, so that's just taking the sum. Okay, so sometimes, and I would say almost always in practice, your algorithm is a little bit more complex than just counting words in sentences or whatever, and you need more than one MapReduce phase. So you have several MapReduce phases, one after the other. And you can do that, so you can use the output of the reduced phase and again take it as input for the next one. And if you do that, you have, and that's shown in the figure below, you have this kind of graph. And so you have dependencies, and where you have your input data, you go to a map and reduce phase, and that's again the input for another phase, and you can have two of these phases and then take both as inputs and so on. And so we call that a DAG, or a directed acyclic graph. And so it's like a network of tasks that depends on each other. And so one disadvantage, and it's an important disadvantage of MapReduce, is that after each MapReduce phase, you store the results. And so the good thing about that is, since you store them, you're sure your data is safe, because that also means your data will be partitioned, replicated. And so that's a good thing, but it also makes things slower, because in the next phase, you're going to read again those results from disk. So that's one downside of MapReduce. Another downside is that you are responsible for an efficient implementation of all these steps. So MapReduce is run efficiently by the framework, but the entire program with all different steps, that's something you have to program yourself, that's done in an efficient way. And then we go to Spark. So Spark is an extension of MapReduce, and to repeat the last point, so it's generalizes easy to more complex directed acyclic graphs. So that means if you have an operation that consists of several MapReduce steps, one after the other, then in Spark you define it, and then you have a single program, and Spark has a global view of this process. And this has advantages. For one thing, Spark can optimize that. For instance, assume you have a map and then a filter operation. So maybe if you define that, first you map and then you filter, Spark will know that because you define it in Python using PySpark or something, and then it can choose to first perform the filter operation and then only perform the mapping. That's maybe more efficient. For instance, if you have word count and you want to filter all words starting with A, then if you first map and then filter it, then you first have to map all words. Well, if you first filter on all words starting with A, then the key value list of all words will be much smaller. So Spark is smart enough to do that and is able to perform perform your data processing pipeline more efficiently. Second thing about Spark is that it uses an RDD data set, RDD kind of objects to represent data, and so that's more efficient than in MapReduce. So in MapReduce, you store all results to disk after you have processed it, and in Spark, you can cache it. So you can keep the entire data set in memory, which is much more faster, especially for machine learning algorithms, where you maybe do multiple iteration, such as batch gradient descent or something like that, multiple iterations over your data, and you do not want to store your data after each iteration to disk and then load it back in, because transferring data to disk and then reading it back from memory, that's an order of magnitude more slower than just keeping it in memory. So Spark does that. And note that this resilient distributed data set is something special, because actually it's a concept. Because behind the scenes, that means that it is you can look at it as one big vector or one big key value list in memory, but actually it's not in memory. It's distributed in the memory over the different nodes. So it's really something special. Okay, this is a picture of the architecture. So it's a little bit similar to MapReduce. You have your yarn master nodes, if you want, so that manages the resources, and then you have all these worker nodes. So each worker node contains Spark, can execute part of the map and reduce functions locally, and then you have the master, the application master, which also contains the Spark contexts that coordinates between all those different nodes. So what are some core components of the Spark API? So you have Spark, it's an API, actually it's in Java, but you have many bindings. For example, we use PySpark, which is a Python binding for the Spark API, but there are also different programming language like Scala, which is specifically designed also for running for writing distributed programs and so on. But what are the components of the API? Well, you have the Spark context, and this is the main entry point to your Spark engine. So with the Spark context object, you can define and submit your jobs. So each job consists of multiple map and reduce functions that you call over the data. Then you have your RDD, so it's where your data is. And it exposes the map and the reduce by key methods. So you can think of it like programs like an ordinary object, and you call functions on it. Of course, behind the scenes, it's distributed, and you're doing parallel processing and distributed processing, but it kind of looks like a regular objects in Python. Also, difference between map reduce is you have map and reduce by key, but you have many more methods. For example, join and all these other methods, which we'll see if I have time at least. It's also something we will practice during the lab session this afternoon. Then you have many more extensions. We're not going to have time to explain them all, but you have SQL Spark sessions. And it's actually an engine for running SQL queries. So also SQL queries, they consist of a select from where group by clauses. That's something you can also express with Spark. You have also the SQL data frame package, and there you have a data frame like objects, but which is very similar to Pandas. So the Pandas data frame library. But behind the scenes, it's also distributed. Then a third useful extension is MLlib. So it's a machine learning library. So it contains a lot of classic algorithms you also have in scikit-learn. But the difference is it's also distributed. And so algorithms for classification, clustering, regression, and recommendations. And then finally, you can use Spark for batch processing, but also for streaming processing. So that's also interesting. Okay, here's an example of indexing web pages using Spark. So it's like your own Google, because you have a lot of web pages as inputs, and then you can create an inverted index. So that means for every word in each web page, you create a link between that word and the URL of the web page that contains it. So you could use that and then create your own Google. Since it's a Spark program, if you have thousands of computers, you can do it for a massive amount of web pages. So here's an example. So assume you have a tab or comma separated file where the first column is a website and the second column is the content of a website. Then you can make this inverted index or word index that maps each word to the web pages in which it occurs. So that's what Google uses behind the scenes. So if you search for a certain keyword, you get all the results that contain that keyword. And of course, Google does more, and it ranks the results in an intelligent way using machine learning. That's not what we're talking about in this example. It's just about creating the mapping between words and URLs that contain these words. For instance, here we have 4 URLs from the VRT news sites, and here's the first 2 articles about Iranian general, And then the last two articles are about escaping from prison and so on. And so we have the word general, and we want to associate it with the first and second link. And we have the word gevangene, which we want to associate with the third and fourth link. So how would the program look like conceptually? So we could have a large list of URLs, and maybe millions of them. Then in the first phase, you would write a map function. You would write a function getTitle and map that on each URL. So getTitle, as input, it gets the URL, and as output, it produces a key value pair containing both the title and the URL. And so the title is retrieved by visiting this web page. And so that's the first task. Then the second task is to split words. So we have the title, we want to compute which words, not titles, correspond with a certain URL. So we can just write a function that splits the title, converts it to lowercase, splits on white space or something like that, return a list of words for each, and associate that with the URL for each title. And so then we have these lists of words and URL for each title, but it's a nested list. And so that means for each article we have a list of words and the URL, but we want actually one flattened list. So that's the next operation. So that's a flatten map, where you create a single list of all the words that occur in any URL and associate it with that, with each word, the URL where it was contained in the title. Okay. And then finally we have the reduce by key, and then a reduce function, which is just joining the lists. So we know for each word in which URL it occurs, and then if we group by words, we get all the URLs of all the articles where the word is mentioned in the title. And we just join these lists, so just append or concatenate these lists. And that's just with the reduce by key and the join list function. The reduction function is just appending each list. So that's the example. Here is the full code. We're running a little bit out of time, so I'm going to skip this, but in essence, you map to get the title, you map to split the words, then you do a flat map to flatten the lists, then you filter. Here, the filter operation is because some words are empty. If you split words in a sentence, sometimes you have a double space or something like that, and then you have an empty word. So you filter those empty words, and then you reduce by key. So that means with the combine URL function, so that means that you are going to create a single list of all URLs containing a certain word. Then you can sort that list, and here I sorted on len pair 1, so that's the length of the second element of the pair, so the length of the value, so that's the length of the list of URLs. So I sort results where a word matches with many URLs. So you can see in Spark, usually you only have map and reduce by key, but Spark has more easy to use functions such as flat map, filter, and sort by, which makes life much easier. Okay, and then we have a little bit more time to go over the different Spark functions. There are two types of functions. We have transformations that transform from one RDD into another RDD. So you can think of an RDD as a list of key value pairs. And if you program it, you can think of it as a single list of key value pairs, but of course in practice that list is distributed in memory over the different nodes. And then you have simple operations such as map, filter, flat map, and also transformations that require a shuffle. And so if you're going to do reduce by key, that means data from a different node with the same key has to be transferred to one node so that the reducer has all the values associated with that key. So that requires shuffling. Same for group by key or join, that's all also similar. And then we have actions. So that's actually, if you write the program in Spark, nothing happens. So if you write map filter, Spark actually doesn't do anything. It's only when you define an action, such as collect or save as text file, that Spark triggers and will look at your entire program, and so all the different steps which are connected in general using a directed acyclic graph, and then it will start evaluating that in a parallel way on different nodes. So you have to be careful that during a lab session, if you just write some operations, nothing happens unless you type collect. With collect, you really force Spark to execute the previous steps you programmed. Okay, so filter. So here we have our Spark context object, SC, and then as inputs here, a toy example, we have parallelize, and then we have this list of 5 integers. So with the method parallelize, you created RDD out of that list. And so that means this list will be stored in memory on one or more nodes. And then we have a filter operation. So it loops over every element, every key value element, well, or in this case, just elements of our lists. And here you say if the remainder by division of 2 is 0, so if it's even, then you want to keep the value, and then the condition is true, and then you keep the value. And then you type collect to really, that's the action that forces Spark to say, okay, execute this, and then you get 2 and 4 back. And so that's an example of a filter operation. And so you could also, instead of this lambda, you can also could define a function, define is even, and there you would say if the remainder of x divided by 2 is 0, return true, otherwise return false. And so lambda is just a way to express that function in line in one statement. Then we have group by key. So group by key will here we have in the example code shown below. We again create an RDD, so a distributed collection of data. In this case of key value pairs, and the key is what A, and then with the value 1, then B with the value 1, and A again with the value 1, and then we group by key. So in this case, A will be associated with the list containing 1 and 2, and then we map the values, and then we compute the lengths. So the map function in this case, or the reduce function if you want, just computes the length of these values, and then you collect that, and then you get the total number of values for each key. Or you can, that's the second example, you can again group by the key, and then you map the values using a list. So that means you store all the values associated with each key in a list. And so A will then contain 1, 1, and B will contain 1. So that's group by key. Join, I'm going to skip for now. It's like joining 2 streams, or 2 RDDs on the same key, similar to joining in SQL. For each, it's like map, but then you can just print something instead of returning a value. And there are many other operations. So during the practice session, we will practice that using Google Colab. And there in Google Colab, you have the options to install Spark. But Dieter will explain that, just executing a couple of lines of code, and then it will install Spark, and then you can start writing your own Spark pipelines. So I do expect that you know this. So also maybe for the project or for the exam, you should be able to understand what these type of programs do, or also provide pseudocode or maybe. So some use cases. I think Google is the classic example where they use MapReduce to index the exploding volumes of web pages. So that's similar to the program I shown before, to create the inverted index and really have an index of billions of web pages. So that was back in 2004. So they in their paper they write that MapReduce has the following benefits. The indexing code is simple, small, and easy to understand. The code deals with fault tolerance, distribution, and parallelization, and that's all actually hidden from the programmer using MapReduce. and it's easy to improve performance by simply adding machines to the cluster. So that's what MapReduce designed to do. And then Spotify also uses MapReduce, and also Spark and things like that. And so Spotify, it's you probably all have or know Spotify. So it's the online service for streaming music. So it has 75 million active users per month, 30 million songs, which amounts to 30 terabytes of data every day. So that's a lot of traffic. And they use MapReduce for reporting, so to pay the bills of artists. They have to count how many times each song was played and so on. And so that can be expressed with either MapReduce or something like Spark. Also for business analytics, for product analysis, for instance, yeah, they can look at the traffic after an A/B test. So that's maybe two different algorithms shown each to a group of users, and then see which button works best. Is it they can have like show half of the users, they can show a button download, the other half is it okay to listen music, and then they can select in the interface what the users are most likely to click, something like that, to further improve the products and the end user experience. And also, yeah, features for data analysis or machine learning, and like the similarity between artists, which also for recommendations, users who like this song also like that song, things like that. You can define a Spark program that computes this and then run it on the 30 terabytes of data and execute it in parallel and distribute it without actually making a lot of effort. Okay, this concludes my presentation. There's some additional information about matrix vector multiplication that's maybe useful to look at during the practice session this afternoon. Any more questions? Was it a little bit clear to anyone? Referring to lecture 2, right, Charlotte. Referring to lecture 2, one could say that only parallel computing consists of different threads. Am I right? Distributed computation doesn't consist of any threads. So, the main thing with parallel computing, you're using different cores or different threads. With distributed computing, you're using different servers, but also each server has multiple cores. And like here in the examples I've shown you, if your Spark cluster contains of a single CPU and you're doing something like a map function, it will parallelize it over different cores of that single computer. So it's both. So distributed computing considers all resources. I hope that's clear, Charlotte.
Okay, so if I understand it in the right way, both are consisting of threads then.
Yeah, we distribute. Yeah, no. A thread is a concept for parallel computing, but you can only start threads on one computer. So you can say MapReduce is indeed the distributed way of doing something like threads, in the sense that you can run the same operation in parallel on different partitions of the data. But if you program yourself, if you have a multi-threaded program, that means you're going to use all the cores of one CPU. And like if you're using something like MapReduce, that means you can execute your program on different computers, so that's not possible with threads, but also that on each computer, each worker in your cluster, there it also uses parallel computation. So there internally, Spark and MapReduce will also use multiple threads within each worker. Just to be clear.
Okay, yeah, that's clear. Thank you very much.
Okay. Any other questions? No? Okay, then I think our time is up. Thank you for listening. And next week will be the final lecture on recommender systems. And then it will be about half of the lecture. And in the second half of the lecture, I will introduce the different projects that there are. And then in the following month, we will work together using all of the techniques we have covered the past few weeks, and do a small project hands-on. Okay.